Okay, welcome friends to this class, and in this class basically we will study the approach how we can find out how we can solve the MDRE, matrix differential Riccati equation, or ARE. So first, if you recall, in the previous class we have seen that my algebraic Riccati equation is A transpose P plus PA minus PB R inverse B prime P plus Q equal to 0. So, this is my algebraic Riccati equation, and the nature of this equation is it is a non-linear algebraic equation, and the solution of this equation is not direct. Sometimes we will have the multiple solutions. So, today we will see how to solve this Riccati equation. So, the first approach we take is the iterative approach. The iterative method to solve this algebraic Riccati equation. Say, if you recall this A transpose P, we can write in the form A B R inverse B prime P transpose P plus P A minus B R inverse B transpose P So, once we are proving the A minus Bk to be stable, then you can recall we have written this ARE in this form. Now, as a iterative approach, what we say, let us give the kth iteration to the P inside the bracket and the k plus 1 iteration to the P outside the iteration. This means we write this as A minus B R inverse B prime Pk P k plus 1 Pk plus 1 A minus B R inverse B prime Pk as minus Q plus Pk B R inverse B prime Pk. So, this is my, I can say, is my iterative equation. So, I will start with the initial guess of the Pk and solve this equation for Pk plus 1. So, I will get the next value of the Pk. So, I can start with k to be 0, 1, 2 and so on. So, we have to note down here, note So, what we are saying, see we have write this as my iterative equation. So, this means for k equal to 0, that will be my first choice, k equal to 1, when k equal to 0 I am finding the P1. So, this equation I write this matrix A minus Bk as, I can write this AK Pk plus 1 plus Pk plus 1, sorry, AK prime Pk plus 1 Pk plus 1 AK as minus Q plus Pk B R inverse B prime Pk, and I start my iteration to be k equal to 0. So, this matrix A0. So, to converge my solution to a constant matrix of the P, I have to select my initial guess should be such that, so P0 I have to guess. So, P0 value should be such that my matrix A0, A minus B R inverse B prime P0 should be a stable matrix. This means this matrix will have its all eigenvalues with negative real part. So, if I will start with this, then my I have to ensure that Pk plus 1 is less than or equal to Pk, and as limit k approaches to infinity, my Pk approaches to P a constant matrix. So, we can see this may be one of the approach to find out the P. We will set a iterative equation as A transpose k Pk plus 1 Pk plus 1 Ak equal to minus Q Pk B R inverse B prime Pk. We start with the first iteration at k equal to 0. This means we first have to find out the A minus B R inverse B prime P0, and we select P0 with my initial guess such that my A naught matrix is stable. I have to ensure Pk plus 1 is less than equal to Pk, then as k approaches to infinity. So, after the few iteration we find that my P value is a constant value. As P will become constant, we will stop the iteration, and that will be my choice for the P, which is my Riccati coefficient. So, by this method we can find out the Pk. My another approach is, as given by the title of this lecture, is analytical solution of the matrix differential Riccati equation using a state transition matrix approach. So, by this state transition matrix approach we can solve the matrix differential Riccati equation or algebraic Riccati equation. So, first we will see to find the solution of the matrix differential Riccati equation. If you recall, we have considered a system x dot equal to Ax plus Bu, y equal to Cxt, which is, and performance index as half of x prime Tf f of Tf x of Tf x prime Qx plus u prime Ru. So, this means first we will consider the case of a time varying system. So, in case of the time varying system of finite time. So, time varying system finite time regulator problem we are seeing in which we will encounter with the matrix, differential Riccati equation, and its solution we have to find out. So, you can recall, once we are solving this system by the Hamiltonian approach, we first write the Hamiltonian, then write the control equation del h by del u equal to 0, which give me the control relation, and state and the co-state equation. So, the state and the co-state equation I write in the as a Hamiltonian system, which is, so I am writing my Hamiltonian system or canonical system in the form of x dot of t, lambda dot of t, which is the set of 2n equation, is A minus E, E is B R inverse B prime. So, here we write A minus B, so it is a time varying case. So, all my matrices are function of time, B R inverse B prime is my E minus Q minus A transpose lambda t, x t lambda t. So, now if we will see my these two equations, so this Hamiltonian system can, if I know x 0 and lambda 0, so this system I can directly solve in terms of the state transition matrix. So, I write this matrix as my Hamiltonian matrix delta, and this I will take it as x t lambda t. And what is the delta? Delta is nothing but a 2n by 2n matrix, because x is n cross 1, lambda is also n cross 1. So, the size of my Hamiltonian matrix is 2n by 2n. And so, if you will see, this is the first order 2n first order differential equations which we have to solve, subjected to the initial condition as solve these 2n number of equations with boundary condition as what the conditions we have? We have x t 0 as say x 0 and lambda t f as f of t f, x of t f. So, in case of the state we are given with the initial condition, but in case of the lambda we are given with the final terminal conditions. So, with this terminal condition our objective is to solve these 2n number of the equations. As we know, with this the solution of this equation can be written as, to solve this, let phi t t 0 be the state transition matrix of Hamiltonian system. This means we are considering phi t0 to be e to the power lambda t. So, if I have my Hamiltonian system this, the state transition matrix of Hamiltonian system is defined as the phi t0, which is equivalent to lambda, sorry, delta t minus t0. Let us partition. So, we write phi t0 in partition form as phi 11, phi 12, phi 21 and say phi 22. Now, say lambda t0 which is unknown. Say lambda t0 be the initial value of lambda t. So, what we can write the solution for the Hamiltonian system? What will be my xt and lambda t? From the linear control theory, this is nothing but my phi t0 x of t0 lambda of t0. So, this means we have considered that the lambda t0 is known, then I can write the solution in this form. By this, if I will write if I will determine the initial condition xt0 lambda t0 which is nothing but my phi inverse t0 xt lambda t, and phi t0 I can write as nothing but phi t0 t. So, this is the identity of the state transition matrix. Phi inverse t0 is phi t0 t, which I can write in terms of the xt lambda t. So, now if we will select the t0 to be any given time and t to be my final time, so I can write my solution in terms of the final time. This means I can also write this as x t lambda t as phi, t0 is my t2, tf, x of tf, lambda of tf, while phi t tf I can write as phi 1 1 t tf, phi 1 2 t comma tf, phi 2 1 phi 2 2 t comma tf multiplied with x of tf lambda of tf. So, I can write my x t lambda t in terms of the tf by this expression. So, I will keep the last equation. Now, if I will expand this relation in terms of the x t, what I will get? Phi 1 1 x t f So, I write this as phi 1 1 x t f plus phi 1 2 lambda t f and what I have lambda t f is f of t f x of t f. So, I will replace lambda t f by this. So, I can write phi 1 1 plus phi 1 2 and lambda t f is f of t f and x of t f I am writing outside. So, taking by replacing lambda t f by f of t f x of t f, substituting here. So, I can write x t as this form in terms of the x of t f, and by this x of t f I can write as nothing but phi 1 1 plus phi 1 2 f of t f. If I have to write x of t f in terms of x t, this inverse x of t. So, from the first equation x t we have expanded from here as phi 1 1 x phi 1 2 lambda, we replace the lambda t f by f and then we are writing x t f in terms of the x t. Then we expand lambda t, which is by this we will get phi 2 1 x of t f phi 2 2 lambda of t f. So, by expanding lambda t by this expression we get this phi 21 x of Tf, phi 22 lambda of Tf. Lambda of Tf we are replacing by this f of Tf x of Tf, and you recall what was our substitution? Lambda t we have taken as the Pt xt. So, lambda t we are writing as Pt xt, and here phi 21 plus phi 22, in place of lambda Tf we have f of Tf, this is multiplied with x of Tf. Now x of Tf I can write in terms of the xt from here. So I can write this as phi 21 plus phi 22 f of Tf, in place of x of Tf I write phi 11 plus phi 12 f of Tf inverse xt, and this is nothing but my Pt xt. Xt we can cancel out from both sides. So my Pt is nothing but phi 21 plus phi 22 f of Tf, phi 11 plus phi 12 f of Tf inverse. So this matrix differential Riccati equation and this Riccati coefficient can directly be find out by this, where phi 11, phi 12, phi 22, phi 21 are nothing but the partition of my state transition matrix. So if I know my state transition matrix, I can partition it as phi 11, phi 12, phi 21, phi 22, and if this is known to me, I can directly find what will be my Riccati coefficient. Riccati coefficient is known to me. This is for time varying case, or we can say this is for the finite time case. For infinite case, for infinite time, basically my terminal cost will become 0. So f of Tf will be 0. So for infinite time, my P nothing but will be phi 21 phi 11 inverse. So this is the another approach by which we can find out the Riccati coefficient matrix Pt for time varying case, or for the finite time regulator case, and P for the infinite time regulator case. So I stop it here for this lecture. In the next lecture we will take up the one example based on this approach, and another method to find out the analytical solution of this matrix differential Riccati equation, which is based on the similarity transformation. and particularly on the eigenvalue and the eigenvector approach. Thank you very much.